Hello students, so we are gonna study equilibrium. So let's start. Now what is equilibrium? Equilibrium is the reversible state for any process at which concentration of reactant and product does not change. Okay, so what does that mean? That means, let's suppose this is a container, closed container. Okay, so in this closed container there is, suppose this reaction is happening. Now, according to the definition of equilibrium, this N2 plus 3H2's total concentration is equal to this ammonia's total concentration at any temperature or whatever the conditions will be, it will be, concentration will be same. So that is the criteria for equilibrium. Okay. Now, this equilibrium has a property. First one is, this equilibrium can only be achieved in closed containers. Okay, I have shown you this figure into a closed container. Now many of you are thinking, what happens if it's a open container? That is, if you do the same reaction in a open container, then think that this N2 is gas 3 and H2, that is also gas. NH3 is also gas. So if they are reacting and forming ammonia, so because of it's a gas, so it will go out, right? So if it go out, then can be the concentration of N2 and 3H2 and NH3 be same at any condition? That can't be happening, because it is always go out after the formation of ammonia. So it will be always a forwarded reaction. It can never achieve the backward reaction. Okay, so it always have to be a closed container for achieving the equilibrium. Now there are two types of equilibrium. That is, there are two types of equilibrium. One is our physical equilibrium. Second is our ionic equilibrium. Now we are gonna first discuss about physical equilibrium. Okay, so let's start. In physical equilibrium, you are gonna see three types of equilibrium. Okay, so let's write that. First one is our solid liquid equilibrium. Solid liquid equilibrium. I'm writing in its short form. Okay, so here what happens, that rate of fusion is equal to rate of freezing. Okay, now for second case, that is liquid gas equilibrium. Liquid gas equilibrium. Here what happens, that rate of vaporization is equal to rate of freezing. Okay. So the third one will be solid gas equilibrium. Solid gas equilibrium. So what happens here? That is rate of sublimation, rate of sublimation equal to rate of solidification. Okay, rate of solidification. Now let us suppose that pressure of A is PA, pressure of B is PB, pressure of C is PC, pressure of D is PD. There is a law called law of mass action. Okay, this is a very important law according to physical equilibrium. So to understand this, we first have to write a equation. So let's write, that is small a capital A plus small b capital B, small c capital C, small d capital D. Now this A, B, C, D all are coefficient. That means suppose we have writing 2NH3. So here 2 is coefficient. So then just like 2, here A is also a coefficient. Now the rate of reaction is directly proportional to the product of concentration of reactant each raised to their power in stoichiometric coefficient. What does that mean? That means if I write this, okay, and let me write this also, okay. Now just what I have told you right now, that is what I have written in the mathematical form. That is this reaction rate or rate of reaction is proportional to the concentration to the power its coefficient. Okay, here you can also see it, but I have written it RF. What does the F mean? What does this B mean? F means forward reaction, okay, and B means backward reaction. That means if CCDD reacts and forms AA and BB, then it will be backward reaction. And if AA and BB reacts and forms CC plus DD, that will be our forward reaction. That's what I have written here. Now we have to remove this proportionality sign. To remove that, we are bringing a constant, that is kf, and let's write the equation again. And for backward reaction, that will be the same. and here it is. So what happens that at equilibrium, to achieve equilibrium, this rate of forward reaction must have to be the rate of backward reaction. Okay. So what happens? These two reactions will be equal to each other. Okay. So it will be like this: k forward by k backward equal to c to the power c, d to the power d, a to the power a, b to the power b. Now this kf by kb can also, and both are constant, so it can, so we just take a single constant for this, that is our kc. Okay, then we write this c to the power c, d to the power d, a to the power a, b to the power b. That's how it is written. Okay, so from this we have learned how to write the kc of a equation. Okay, now let's see what is the degree of dissociation. Okay, degree of dissociation. Now degree of dissociation is denoted with alpha, and its formula is number of moles dissociated by initial mole taken. Okay, now what does this mean? That is, let's say in a reaction we took 3 moles of N2. Okay, so here this is not the coefficient. Okay, and 2 moles of H2. Again, this is not the coefficient. So what happens if we write this? That this is taken 3 moles, this is taken 2 moles, but it is 0 because at initial position, or initial mole, this NH3 will, is not there because it hasn't started the reacting yet, nitrogen and hydrogen. So the initial mole of NH3 is taken 0. But after the reaction is done, what happens? Let's assume that N2 has, now let's write the moles after the reaction is formed. So now we're going to see that what is this X? This X is the moles of the N2 what involved in the reaction to make this NH3. So the rest of the moles are here, or remaining N2. So plus this thing, that is 3 my 2 minus 3x. So you can see that when we are writing this x, so we have to add it, uh, the coefficient of this equation, and here we also gonna write like this 2x. So from this that X is the moles got involved, that that means number of moles dissociated, and this 3 is the initial mole. So if we write X by 3, so that will be our alpha. Also we can write it like this, that is 3x by 2, that will also be alpha. Okay, now in neat questions they gave you the value of alpha. Let us suppose it is given to you 0.5. Okay, so what happens that uh, this we can write it like half, because alpha here given is 0.5. So you can just see that here the value of x, okay, will come as, let us suppose this, if we take this equation, so the value of x can come like this, so it will be our 3 by 2. So if we just minus or subtract it from 3, so the mole of N2 after reaction we can get it, and also can get it for 3H2 2NH3. So from that we can write its Kc, right? Just we have written it in the previous example. Okay, that's how. So this is how you write or conclude alpha, and from alpha you can conclude the moles, and from the moles you can write the Kc of a reaction. Okay, so it's done. Now next is our Kp. Now what is Kp? That is we are gonna write. Okay, Kp is the reaction constant but with respect to pressure. Okay, so let's write it. Let us suppose there is this standard reaction. Okay, we are gonna use it open. So what will be the Kp? Kp will just replace the concentration term with the pressure term. That will be Pc to the power C, Pd to the power D, Pa to the power A, and Pv to the power B. That's how we write Kp. Now from this we can also derive the relation between Kp and Kc. That is, if we write it like this, and here also, now all of you are thinking that what happened here. So we know that C, A, B, and D, these are concentrations. So we all know this formula, that PV equal to nRT. Now what happens when we write this N by V into RT? Okay, it becomes P equal to concentration into RT. That because moles, that is N by volume, equal to our concentration. So that's how we have written it here. Concentration into RT, concentration into RT, concentration into RT, concentration into RT. So if we separate this equation from like this, okay, it's just a derivation. You guys don't have to take pressure on it if you are feeling that, oh my god, we have to remember it. No, you don't have to remember it. After the solving this equation, there comes a form. That form you have to remember, not this derivation. But I am just showing this derivation it because of your understanding. Okay. So from the previous, we can also write it like this, because that CC into DD, that will be our KC, and RT what we have just separated from that equation, that comes our del NG. Now we all know what is this del NG. That is our moles of product minus moles of reactant. Okay, that's how what we have written there. So del NG comes from this. Now from this equation, there comes some relations. So this equation is very important. That's what you have to remember, not the derivation. Okay. So in case 1, what happens if this del ng here is equal to 0, then our Kp is equal to Kc. But what happens if this del ng is greater than or less than 0? That's why we're gonna write. Let's see what happens in del ng is when less than 0. That's when our Kp becomes less than Kc. But when del ng is greater than 0, Kp becomes greater than Kc. We can just see or verify from this equation. Okay. So that's how Kp and Kc is done. Now Kp, after Kp and Kc, there are some properties of equilibrium. So let's see that. Here, properties of equilibrium. That is, just like the thermodynamics, we have some properties in equilibrium also. That is, if these equations Kc, suppose K1. So if we reverse the reaction, what happens? Don't confuse it thermodynamics. Okay, because these two are totally two different things. It becomes 1 by K1. Okay. Now what happens if we multiply with it with 2? Then this K dash becomes K1 to the power 2. Okay. And also in Hess's law, we have seen that if we do this, let us suppose this is K1, this is K2, this is K3, and this is K. So in Hess's law, we have seen we can just add this K1, K2, K3, but here in equilibrium, we can't add it. Okay. What we have to do for this K, we have to write it like this. K1 into K2 into K3. That means we have to multiply it, not add it. Okay, these are the things we have to remember, because everyone just confuse it with thermodynamics and make mistakes. So let's see a problem regarding to this. Okay, so let us see a easy example on this. That is, if they give you this equation 2a plus 2b to 2c, that its equilibrium constant is k, but if c greater than this, then, and if its equilibrium constant is k equal to 10. Okay, then what's the value of this k dash? We have to conclude it. So what we are gonna do, we are gonna write this equation in form of this equation. So if we write that, what happens? Let's write it k1. It will be 1 by k, right? Because we have seen that if we reverse the equation, this its form, its coefficient will be, or its reaction constant will be like this. So it will be 1 by 10. Now if we multiply it with 2, we know it goes, it it's on its power. Okay, so what will be it? It will be 1 by 100, and that is our answer for this. So we have seen an example. Now comes a very important principle regarding to physical equilibrium, that is our La Chatelier's principle. Okay, so what does this principle say? Let's write it. If any of the factor is changed at equilibrium, is changed at equilibrium, then the reaction will shift in that direction. Then the reaction will shift to that direction where it can counterbalance the change applied, where it can counterbalance the change applied. Okay, so what does this mean? That's we're gonna uh, learn now. So let's learn this. What happens that, first let us see it for concentration. Okay, so you're gonna write again that standard equation here. Now suppose in a equilibrium condition, this concentration of A and this concentration of B is increased here. Okay, so if it gets increased, so what will it do to achieve the equilibrium condition? It has to make its concentration same with this CC and DD. Now what it will do, it will increase its rate of forward reaction to make more C and more D, to make its concentration same with C and D, because its concentration we have increased, so it will make more C and more D, so its concentration will decrease when it will react, and CC and DD will, its concentration will increase. So at some point, what happens, this concentration of, decreasing concentration of A and B becomes same with the increasing concentration of C and D. That's when the equilibrium is again achieved. Okay, so that's what we're gonna write here, that is, if the concentration of reactant is increased, okay, so the reaction will go to forward direction. and you can just guess it. If the concentration of reactant is decreased, then it will go to backward reaction, right? But what happens when the concentration of product is increased? Same case happens, that it in for its increased concentration, it want to make its concentration same with its reactant. So what will it do? It will go backward reaction. So that's why it concentration then decreases and its concentration increases, and then at some point their concentration becomes same and they achieve the equilibrium again. So concentration of product is increased. What happens? It goes to backward reaction. And if concentration of reactant, sorry, concentration of product is decreased, then it goes forward reaction. Now, for exam purpose, we just have to remember these two, because the opposite case will happen in here. Okay. So just remember, if concentration of reactant is gets increased, it will go forward direction. If concentration of product is increased, it will go backward reaction. And if the opposite case happens, then you just assume the opposite. Okay. Now, what happens in case of pressure? That is, this pressure has three factors. Okay. That is, if del Ng equal to 0, then this pressure will have no effect on the equilibrium condition. But if del Ng is less than 0, okay, so what happens? That means that pressure is increased. Okay, so let's write it. If pressure is increased, then reaction goes to that direction where number of moles is less. Okay, and what happens when del Ng greater than 0? That means the pressure is decreased. So if pressure is decreased here, so reaction will go to that direction where number of moles is increased or more. Okay. So let's see an example. You will understand better. Suppose there is the equation PCl3 plus Cl2 PCl5. Now, what will we have done here? We have increased the pressure here. Now, you can see, if we increase the pressure, now the neat question they will ask you that where will the reaction go? It will be forward reaction or it will be backward reaction. So you can see that if we just count the number of moles that of the reactants, that is 1 plus 1 2, but the product has 1 mole, that is of PCl5. So I have told you, if the pressure is increased, the reaction goes to that direction and number of moles is less. So here we can see the product number is less, so it will be our forward reaction. Okay, but what happens if the pressure is decreased? Then we can see that reaction will go to that direction and number of moles increases. So we have reactants and more number of moles than the product, so it will be our backward reaction here. Okay, so here we have seen an example. Now comes the third factor, that is our temperature. Now in case of temperature, we have a very easy and simple thing. Okay, you have to remember two things on it. Okay, so don't remember their opposite version because you will confuse in exam. Okay, so let's see, that is, if temperature is increased, then what happens, that in case of endothermic reaction, you all know what is endothermic reaction, we have studied in thermodynamics. So endothermic reaction, it becomes forward reaction. Okay, but if temperature is increased, but it is our exothermic reaction. Okay, so the reaction will be backward reaction. Now many of you are thinking that why is it happening. I'm going to explain you that. Suppose there is a reaction AA plus BB CC plus DD. Now this reaction is exothermic. That means when the reaction is happening, it is extracting or excluding or emitting some heat. Now if the temperature is increased, so what happens, that already is it is extracting more heat, then now we are giving also heat from outside. So what happens, the reaction, forward reaction, gets hindered. And what happens then, if forward reaction gets hindered, then the backward reaction comes into play. That's why in exothermic reaction, if we increase the temperature, it will go backward reaction. Now think that this is the opposite case. That means it is an endothermic reaction. So when it's happening, the forward reaction, that means the reactants are forming the product. Okay, it is absorbing heat from outside and we are giving it heat from outside. So what happens, the forward reaction gets more power there, right? So in endothermic reaction, if the temperature is increased, it favors the forward reaction. But you can just guess it, that if the temperature here is not increased but decreased, then the endothermic in case of endothermic reaction, it will be backward reaction. If the temperature is decreased, then the exothermic reactions case, it will be forward reaction. But we won't remember that opposite things here because it will be very confusing in exam. Okay, so we'll just remember these two standard cases and it will be enough.